My name is Simon, as Tyler had introduced. Currently third year. I've been through your 137, 138 courses. Actually, I took the 148 version of it. But hopefully, what I'm going to do is I'm going to go over the concepts and the different topics that were covered before the midterm, and also give you guys hopefully lots of examples in terms of the techniques of integration and the areas and volumes of solids, as well as the differential equations and improper integrals. Alright, so without further ado, let's get started. So obviously, if you guys have any questions throughout the session, just please don't hesitate to ask. You can interrupt me anytime by raising your hand but I'm explaining a question right now. Can people at the back hear me right now? Yeah, everything's good? Alright. Also, don't be intimidated because I'm wearing this. I just had an interview, so it's not my original. So I'm going to begin by talking about a little bit just about integration itself to make sure that everybody is fine with notation. So integration, what is integration? It's the reverse operation of differentiation. And when we write an integral, we denote it as integral fx dx. I just wanted to make sure everyone is familiar with the term integrand. And this entire thing, the operation right here is called the integral. So when I'm referring to the integrand, I'm referring to the function that's inside of the integration. All right. So usually integrals and derivatives are very interconnected concepts. So just keep in mind that as we walk through the different techniques of integration, that technically, if you can recognize what function has the derivative that's inside of the integration sign, you can technically immediately figure out what the antiderivative is, right? For example, if you recognize that the derivative of ln x is 1 over x, then integration, obviously, of 1 over x is ln x. Just something very obvious, but it's going to be a key concept as we talk through this. So I'm going to start with the first technique of integration, which is integration by substitution. So recall that when you probably took Math 137 or from your high school calculus courses, that the chain rule of differentiation is that d over dx of f of g of x is equivalent to f prime of g of x plus, multiplied by g prime of x. And integration by substitution is the exact reverse of that. So now let's try to integrate f prime g of x, g prime of x dx. Now if we let u equal to g of x and du over dx, then it's going to be g prime of x. This implies that du is going to be equivalent to g prime of x dx. All right, so we have this part right here, which is essentially the derivative of what's inside of this function right here. And then we have this integral translates to integral f prime u du. And that will give us f plus. So that's the basis of integration by substitution. So what is the key of integration by substitution? We need to recognize the integrand as a product of u and its derivative, and perhaps sometimes the u instead is a function of itself. And once you have that, we make a substitution using u equals g of x, convert the function to a much more easily integrable form, and then which we can directly figure out the derivative, the integral from, and then we would need to make the substitution back. where u is equal to g of x. So I'm going to write down 3 steps here. The first step is to recognize the integrand as a product of f of u and its derivative. U and its derivative. U for a function. Derivative, and the second step is to substitute, to integrate with respect to u. And the third step is to, after you finish the integration, substitute u equals g of x back into the expression. I just wanted to give you guys a systematic idea of what exactly to do when you're integrating by substitution. So this may seem a little bit abstract, so let's walk through a few examples. Yes. Integral x squared plus 1 q x dx. So as I said before, yes?
Sam, can you just write a bit bigger, please?
A bit bigger?
Yeah.
All right. Will do. Thanks for pointing that out. So as I said before, to recognize when to use the integration by substitution, we need to recognize the integrand as a product of something and its derivative. And in this case, we see that x squared plus 1 has the derivative 2x, which covers the entire integrand. And that's when we can use the integration by substitution by letting u equals to x squared plus 1, and then du over dx is going to be equivalent to the derivative of this, which is 2x, which implies that du is going to be equivalent to 2x dx. Now this may be a little bit confusing. What does this du thing exactly mean? For now, this is not exactly very rigorous notation, but I found it very useful when you're doing integration by substitution, or by parts for that matter. So what's happening is that these are called differentials, and these are the things that appear at the end of an integral sign. And all you need to note is that this kind of thing, all you need to do is derive it, and then move the dx to the other side. And this will allow you to get rid of the dx inside of the integral sign. So let's continue with the integration. It's going to be equivalent to integral of u cubed du, because 2x dx, as I said right here, is du, and x squared plus 1 is u cubed. And this is obviously a very easy integration to do. It's going to be u to the power 4 over 4 plus c, which is going to be equivalent to, and now this is the second step of what I said before. This is the integration step. And then the third step right here is going to be substituting u equals the expression of x, which will give us x squared plus 1 to the power 4 over 4 plus c. And never forget about the concept of integration when you do these integrations, because you can get dot marks. So that was a very easy example. And now I'm going to move on to an example that showed up in your first assignment, the question 5 of your first assignment. Is this large enough?
Yep.
Yep. So again, we want to recognize the integrand as a product of an expression and its derivative. Right? As we see, these kind of recognition comes through practice, but you can probably see that 2t squared plus 3t derivative is 4t plus 6t. And in this case, 4t plus 6t is equivalent to, multiplied by 2 is equivalent to plus 3 is equivalent to the expression right here, at plus 6. So if we let u equals to 2t squared plus 3t, then du is going to be equivalent to 4t plus 3. And this is going to, this integral translates to the integral of u power negative 1 times 2 du. That's going to be equivalent to 2 integral of u negative 1 du, which is 2 long absolute value of u plus c, which is 2 long absolute value of 2t squared plus 3t plus c. So does anybody have any questions so far?
No.
So I'm going to move to some more complicated examples from now on. And the first one I'm going to give is that because the key to all of these integrations is to recognize that the integrand is a product of something and its derivative. We need to recognize, sometimes there are more complicated derivatives of different functions. And in this case, I'm going to give you an example of an inverse trigonometric function. So unlike the other examples, which are polynomials essentially, this one involves an inverse trigonometric function. And just upon first look, it's kind of, we don't really know what to do with this kind of integration. But as long as you realize that d over dx of arc cos x is equivalent to negative 1 over square root of 1 minus x squared, you'll immediately recognize that this expression right here is u and du over dx. And this allows us to do the integration by substitution. Then u equals to arc cosine of x, and du is equivalent to negative 1 over square root of 1 minus x squared. Then this expression will become integral of u du. Last thing to see is compared to this huge bump of thing right here. This is u squared over 2 plus c, which directly translates to arc cos of x squared over 2 plus cos. So, does anybody have questions for this right here? All right, so as I understood from my discussion with Tyler, many of you had problems with trigonometric integration, substitution. So I'm going to move directly to that because integration by parts is the next thing, and trigonometric substitution, strictly speaking, is just using integration by substitution. So I'm going to start with so the idea is to use trigonometric identities to perform the substitution. And I'm going to give you a very simple case here where the integrands are actually trigonometric functions itself. So let's try to do integral of sine cubed. In this situation, we use the trigonometric identity that sine squared is equal to 1 minus cos squared. So this expression simplifies to 1 minus cos squared x, because this is sine squared times sine x. So it's 1 minus cos squared x times sine x dx. And the reason why this kind of substitution makes it simpler is that we realize sine x derivative is cos x, and cos x derivative is negative sine x. So by substituting a part of the expression of sine x here into cos x, we have created an expression which is composed of an expression and its derivative. And we can use this fact to perform integration of substitution. So firstly, we will break the bracket right here. This part directly turns into negative cos x. And the second part right here, we're going to perform using integration by substitution. And it's going to be u squared minus du. If we let u equals to cos x and du will be equal to negative sine x dx. And then you can see that cos x squared turns into u squared, and sine x dx is negative du. And this expression is very easy to integrate. U cubed over 3 plus c, which is equal to negative cos x minus u is equal to cos cubed x over 3 plus c. And of course, one good thing to do after you integrate is always to derive it back if the expression is not too complicated, and to see if you get the original expression. So I'm going to give you right here. To learn this in a systematic way, I'll give you a list of the trigonometric identities that might be used for the trigonometric integration substitution. And obviously, the easiest ones are, as you probably learned in high school, sine squared plus cos squared equals to 1. So that immediately gives us two identities. And then if we divide both sides of the equation by cos squared theta, then we get two more identities where, because noting that 1 over cos is secant, and sine over cos is tangent. Dividing both sides by cos squared, you will get secant x squared theta minus equals to tangent squared theta plus 1. And obviously that tangent squared equals to 1 minus secant squared. Okay. And these will be used very extensively in your trigonometric substitution. And there's just two more formulas that might be useful when you're integrating trigonometric things of even degree. And it's going to be the double angle formulas. 1/2 1 minus cos 2 theta and 6/1 cos squared theta is equal to 1/2 1 plus cos 2 theta. All right, now with those in mind, we're going to move to some examples using trigonometric integration.
Right now it looks pretty good.
All right. Along the same flavor of the last example we gave is integral of sine x dx. I'm not sure if this kind of expression will show up on your exams or has it shown up on your assignments, but in your textbook I found that it's actually specifically dedicated to these kind of integral of sine to the power of something and cosine to the power of something. So I'm going to go over a systematic way of doing it after this example. So when you encounter something like this, directly using one of these identities doesn't really work very well because it gives you 1 minus cosine squared, which is still an expression of this form, and it doesn't really tell you anything further. So instead of doing that, we directly use one of these half-angle identities, And this will become half integral of 1 minus cos 2x. Which is 1 half bracket x minus integral of cos 2x dx. We can perform a simple substitution here, or you can directly recognize the answer. That is easy. That u equals to 2x and du equals to 2 dx. I think something to pay attention to here is that even if you do the direct substitution here, this is equal to u, this dx does not directly go to du. And that's because the derivative of u is not 1. So you need to pay attention to not directly making the assumption that integral of cos 2x is sine 2x. And so these two are not equivalent, and that's one of the common mistakes I think that people make when the inside is a simple expression like 2x. So if we let u equal 2x, du equals to 2 dx, then this becomes 1 half x minus integral of cos, cos u du, which will give us 1 half x minus 1 half sine u plus c, which is 1 half x minus 1 half sine 2x plus c. Okay, now, so for a more systematic way to do this, so we consider the general case of integrating sine x to the power of n and cos x to the power of m. And I'm going to show you in tabular form how to solve these things. Our sine cos and strategy. Suppose the power of sine is even and the power of cosine is odd. Then what we do is we leave one factor of cosine. So this expression will turn into cosine of even power times another cosine. And then we can express all of these using the identity cosine squared equals to 1 minus sine squared. And it's going to be equal to 2. And then this expression turns into a huge lump of sines and one cosine factor. And the reason why we do that is, again, to use trigonometric substitution and the fact that the derivative of sine is directly cosine. So if we let u equals to sine, and du will be directly equal to cosine, and this entire expression can be integrated as a polynomial. So I'm going to write it here. We're going to leave one factor of cos, express the rest cosine, express it as cos squared equals to 1 minus sine squared, and integrate from there. And then use the substitution and use u equals to sine x du equals to cos x dx. And on a very similar note is the situation when the power of sine is odd and the power of cosine is even. We basically apply the exact same strategy. Sines and cosines are like twins or cousins that go alongside with each other. So we leave one factor of sine and express the rest of them using sine squared equals to 1 minus cos squared. And then we use u equals to cos x and du equals to negative sine x dx. One thing to note here is that the derivative of sine x is cos x, but the derivative of cos x is negative sine x. Took me a while to memorize that when I was in high school. Which one is the negative one, which one's the positive one. And the third situation is when they're both even. Then we have to use the half angle identities. So that's formulas 5 and 6, right? Over here. As you can see, these directly decompose an even power of sine and cosine into lower powers of cos, which allows for easier integration. And the example that we did, which I'm not sure if I raised, the integral of sine cubed, was an example of this, where there was sine cubed, right? So we expressed the sine squared factor inside as 1 minus cos squared, and we left an independent sign, and then we used the trigonometric substitution. And the example of sine squared x that we just did right here was a perfect example, the simplest one actually, of using the half angle identities to solve for integrals with only even powers of sines and cosines. And then the last case where you have both odd powers of sines and cosines, you can use either one of these methods. Let's call this 1 and call this 2. Then you can use 1 or 2. Okay, so I think that covers all of these situations. Does anyone have any questions so far? You guys seem a little quiet, eh? You guys all just waiting for the reading week? Yeah? Well, me too, I guess. Alright, so I'm going to give you another example. So as we discussed here, if both powers are odd, then we can either use approach 1 right here or approach 2 right here. Because sines and cos are kind of symmetric to each other. So in this case, because the power of sine is 3, it's bigger than 2, so we can leave out one factor of sine in here and express the other one using the identity. We're going to do so. And then, using the trigonometric identity, number 1, this is 1 minus cos x sine x, cos x, x, which is going to be equivalent to breaking down the bracket, sine x cos x, minus integral of cos cubed x sine x dx, which is going to be, let me just write it here, let u equals to sine x, sorry, cos x, and du is going to be the derivative of that, negative sine x dx. So this entire thing is going to be expressed as integral of u, negative u du, plus, because this was a negative right here, and we're going to have a negative right here, so integral of u cubed du, which is going to give you negative u squared over 2 plus u cubed, u to the power 4 minus over 4, and then plus a constant. And then we can just substitute u equals cos x back, so that gives me, I'm just going to write it here, cos squared x over 2 negative plus cos 4 x over 4 plus c. All right, so enough of that.